Hello students, so today I am going to make one video on the topic piecewise smooth functions, and we'll try to understand how this piecewise smoothness of a function is relevant to the existence or convergence of a Fourier series, and step by step. Okay, so let us try to understand what is piecewise continuous function first before going to piecewise smooth function. Piecewise continuous function. And while discussing about the Fourier series in the previous classes, I have talked many times regarding piecewise continuous function, and we can understand what is piecewise continuous function with the help of a plot. Suppose here it is from minus pi to pi, and I am drawing three pieces of plot in that interval, and so in each pieces, these individual pieces are continuous, means at each point the function is defined. Okay, and what are the acceptable discontinuity, that is jump type of discontinuity. It is jump type of discontinuity, means at this break the both right hand side and left hand side value of that right hand side and left hand side exists, but those are not equal. Means if you take limit, suppose this is the point x naught. Okay, x tends to x naught negative, that will have some value, but that is not equal to the right hand side value. Okay, right hand side limit value. So this type of discontinuities are called jump discontinuities. So if in a interval, in a defining interval, if there are finitely many jump discontinuities, here we have shown three number of this type of jump discontinuities, or sorry, two number of jump discontinuities. So as per the definition of piecewise continuous function, there can be finitely many number of jump discontinuities, that can be 1, 2, 3, 4. Okay, and sometimes it is also called as zero number of discontinuities. If there is no any discontinuities, means there is a single piece of the function defining in interval, then also sometimes it is defined as a piecewise continuous function, because there is zero number of discontinuities and in that defining interval. Okay, that is another point. So now we'll not see this point, but remember there can be finitely many number of discontinuities in a defining interval, then we'll call this a piecewise continuous function. Okay, so now what is piecewise smooth function? Piecewise smooth function, we define or we say function piecewise continuous seeing the nature of that curve of fx. Okay, and unlike that, while talking about piecewise smooth, we see the nature of the derivative plot f dash x, first derivative plot. So we can understand that thing with the help of example. Suppose this is the plot of fx is equal modulus of x from minus pi to pi. Okay, if you, this is the function fx. If you plot the derivative plot of this function, and it will look like this for this, and from positive direction it will be looking like this. This value is 1, this is from minus 1. Okay, so here if you see in the derivative plots, there is a jump discontinuity at x is equal to 0. Type of discontinuity we discuss here. Here we are getting this type of jump discontinuity in the plot of first derivative plot f dash x. So now if this is the case, means here I am showing only one jump discontinuity, but there can be more than one. That means there can be finitely many this type of jump discontinuity in the derivative plot. Then we call this function, this fx, this modulus function, a piecewise smooth smooth function. Okay, we will always see the nature of the derivative plot. We will not see the nature of this function, the nature of this function plots. Okay, so that function plots can be piecewise continuous sometime, means that piecewise smooth function, which is a piecewise smooth function, the function can be continuous or that function can be piecewise continuous also, but we will see only the nature of this derivative plot. That can be understood with the example. Another example, if you plot this function, suppose this one and like this, and it is defining like that, fx is equal to minus x plus 1 for minus pi to 0, then minus pi for 0 to pi. Okay, so this is the fx. So definitely this is a piecewise continuous function. One jump discontinuity is there. So if you plot the derivative plot of this function, that is f dash x, there you will get it is having negative slope, so it is with minus 1, and for this portion it will go along the x-axis. Okay, so here if you see in the derivative plot also there is a jump discontinuity, one jump discontinuity there, so we call this function a piecewise smooth function. Piecewise smooth function. If you see here, the function is also having jump discontinuity and the derivative plot is also having jump discontinuity, but like in the earlier cases, the only derivative plot is having jump discontinuity, but this function was not having any jump discontinuity there, because in that example fx equal to modulus of x, but we will see only the nature of this derivative plot. Okay, so this is the thing. So now in Fourier series we call the smoothness of a function in terms of first derivative or sometimes second derivative. Okay, but a function is normally smooth, or it is called smooth, if a function is having infinitely many derivatives. Suppose e to the power x, if you take the first derivative you will get e to the power x, second derivative e to the power x. You can do infinitely many times, you can do derivative of this function, so it is a absolutely smooth function. Okay, and for example, another example, if I take fx equal to x square, first derivative twice x, second derivative 2, third derivative 0, means after third derivative it is vanishing. So this function is having smoothness of order x3. Okay, so but this function you can do many times derivatives. Similarly for sin x, cos x. So those are the example of absolute smooth functions. So those things we will not discuss here in this Fourier series, but here we will remember the smoothness of a function in terms of the nature of that function of first derivatives, or sometime we will discuss about the second derivative also. Okay, that thing we will discuss while discussing about the term by term differentiation of Fourier series in the later videos. Okay, so uh, I want to show another example, another cases of piecewise of a smooth function. Suppose the function fx is equal to x to the power 1 by 3. If you plot this function, it will be look like this. Okay, from minus pi to pi. So you can ask me whether this function will have any Fourier series or not. Then answer lies on these derivative plots. If you find the derivative plots of this function, okay, if you draw this derivative plot of this function, it will be looking like at x equal to 0 it will go to infinity. In the negative direction it will go to infinity at x equal to 0. Okay, means here it is the derivative plot of that function. Here it is going to minus infinity, here it is going to plus infinity. So at x is equal to 0 there is a discontinuity, but it is this function derivative plot, it is minus infinity and plus infinity. So we cannot call it is a we should not call it is a jump discontinuity. So this function, it implies that this function is not piecewise smooth function. We only accept discontinuity which are jumped type of discontinuity. So it is not a piecewise smooth function. Okay, so this function, since it is not a piecewise smooth function, this function will not have a converse Fourier series. Okay, that is the thing. Since we are talking about the Dirichlet condition at the starting of this Fourier series uh, topic, there we define some conditions that which should which need to be satisfied by a function for its Fourier representation. So similarly, a function should be piecewise continuous to have its Fourier series and to have its convergent Fourier series. Okay, that thing that is very important, and we have understood that thing with the help of this example. Okay, so uh, so in the later classes, we'll try to understand the term by term differentiation of Fourier series and term by term integration of Fourier series. Means if we do the differentiation of a Fourier series, then after differentiation the series will obtain, that will be a Fourier series or not, that thing will understand. And if it will be a Fourier series after differentiation also, then at which condition that can be a Fourier series and at which condition that cannot be a Fourier series, those things we will try to understand. Okay, so in this topic regarding the piecewise smoothness of a function, if you are having any trouble, any questions, then you can ask me in this comment section. Okay, thank you very much.